How are semiconductors tested for quality and reliability? In today's fast-paced world of technology, understanding how semiconductors are tested for quality and reliability is more important than ever. With the increasing demand for reliable electronic devices, this topic is trending among electrical engineers and tech enthusiasts alike. So, how do engineers ensure that these essential components perform as expected? Let's take a closer look at the testing processes involved. First up is wafer-level testing, which occurs immediately after semiconductor wafers are produced. Engineers utilize specialized equipment known as probe cards to establish electrical contact with each chip on the wafer. This initial testing checks basic functions like whether the chip powers on, responds to signals, and identifies any visible defects. Catching issues at this stage helps prevent costly problems later in the manufacturing process. Once chips are packaged, they undergo a series of more detailed electrical tests. These tests measure important parameters such as speed, power consumption, and signal integrity. By simulating real-world conditions, engineers can ensure that the chips operate within their specified limits. For instance, processors may be tested under varying temperatures and voltages to confirm their reliability under stress. Reliability testing takes things a step further. Chips are subjected to accelerated aging tests, which include high-temperature operation and repeated power cycles. These tests help predict how long a chip will function in everyday use. Additionally, engineers conduct environmental stress tests that expose chips to humidity, vibration, and thermal shock. This helps identify weaknesses that could lead to early failures. Modern semiconductor testing also incorporates advanced physical inspection techniques. Methods such as infrared thermography allow engineers to visualize heat distribution across a chip. This can reveal design flaws or manufacturing defects that may not be apparent through electrical testing alone. These techniques provide a detailed understanding of temperature variations, helping to pinpoint potential issues. As chip designs evolve, particularly with the rise of chiplet-based architectures, testing has become more complex. Chiplets are smaller, modular components that combine to create a complete system. Testing these configurations requires new strategies, since traditional methods may not effectively identify problems arising from interactions between chiplets. Engineers must verify both individual chiplets and their overall performance as a cohesive unit. Data plays a significant role in contemporary semiconductor testing. Manufacturing processes generate vast amounts of data, and engineers increasingly use artificial intelligence to analyze this information. By identifying patterns that signal defects or reliability concerns, engineers can make informed improvements to both designs and production methods. Finally, traceability is essential in semiconductor testing. Each chip's test results are meticulously recorded and linked to its manufacturing history. This allows engineers to track down the source of any issues that arise, ensuring that only chips meeting rigorous quality standards reach consumers. Testing semiconductors for quality and reliability is a comprehensive process that spans from wafer-level assessments to environmental stress tests and system-level validation. As technology advances and designs become more modular, testing methodologies must adapt accordingly. Electrical engineers employ a combination of electrical, physical, and data-driven techniques to ensure that the semiconductors powering our devices are reliable and high quality.